This is your presenter Asloob Mudassar, and I am presenting slide number 5 of the course on atomic and molecular physics. In the today's lecture, I shall be covering the following topics, that is quantization of atoms established experimentally, Franck and Hertz experiment for investigation of discrete levels in atoms through inelastic collisions. Quantization of atoms established experimentally. Leonard in 1902 investigated ionization energy of atoms using the experimental setup shown. So this is the experimental setup. And in this experiment, you can see that there is a gas chamber. And the components of the gas chamber are that there is a heater wire which is heating the cathode. The cathode is not shown, and that cathode is connected through this negative terminal of the supply. So the cathode is at negative potential, and the heater wire is connected with a separate battery which is not shown. So the battery is connected to the heater wire, and the heater wire heats up the cathode which is not shown over here. So here is just in front of the heater wire, there is a cathode wire, there is a cathode terminal, cathode plate which is connected with the negative terminal of this battery. So the heater will heat the cathode and the electron emission will take place. The emission of the electron will be through thermionic process. So these are the thermionically emitted electrons, and since the cathode is at a negative potential, it will push the electrons away from its surface. So the electrons will be scattered away from the cathode surface. The second component is the grid. This is the grid G shown in the dotted line. It is like a mesh. So this grid is connected, you see that, with the positive terminal of this supply. So there is an attractive potential between the cathode plate and the grid G. That is, the electrons are accelerated towards the positive terminal, positive grid G. So the electrons will move as shown by these arrows just in front of the cathode, that the electrons arrows are shown. That is, these electrons are accelerated towards the grid G. So in the grid G, you see that this is a mesh type grid. So there are holes in that one. So the electron will penetrate through this grid and will enter into the gas chamber. So here is the gas chamber, and the gas is filled in the chamber at low pressure. So what will happen? You see that in the gas chamber, I have shown spots with green spots, the blue spots, and the red spots. So these red spots indicate electrons. So electrons are indicated by the red spots. Green spot indicate the neutral mercury atoms, or the vapors of these are actually the vapors. Green spots, green dots represent the mercury vapors. So these are the mercury vapors, or you can also say that these are the atomic mercury atoms. After these electrons will collide these green mercury neutral atoms and will ionize them. Once these green mercury atoms are ionized, they are converted into the blue dots, and blue dots mean that they are the ionized mercury atoms. And since these are the ionized mercury atoms, they will move towards the plate because the plate is connected with a negative supply. So due to a negative supply connected with the plate since is a negative potential, so what will happen? These positively charged blue dots, or the positively charged singly ionized mercury atoms will move towards the plate. So when they will move towards the plate, then of course a current is detected. So you see that there are two parameters in this experiment that will be measured. So VG is the grid voltage. So we shall change the grid voltage from the very small value, for example, from the value equal to 0, the grid voltage is changed, and the slider of this grid voltage will be moved towards the right, so that the grid voltage will be increased. So once the grid voltage will be increased, it means that the electrons which are accelerated towards the grid G, they will be moving with more kinetic energy. So they will acquire more kinetic energy, and so the electrons with greater kinetic energy will move into the gas chamber. And due to the ionization, these electrons will collide with the neutral mercury atoms, and if they have sufficient energy, that is, if their energy is greater than or slightly greater than or more greater than the ionization energy which is required to ionize these mercury neutral atoms, then of course these electrons will collide with these neutral mercury atoms, and the mercury atoms will be ionized. That is, its outermost electron will be thrown out of the atom. Under that condition, there will be a positive charge on the mercury atoms, and they will be represented by these blue dots. So blue dots are actually the ionized mercury atoms, singly ionized mercury atoms, and since they have acquired the positive charges on them, so what will happen? They will be attracted towards the grid, towards the plate A, or towards the anode terminal of this assembly, and then of course once they will reach the anode terminal, then of course a current is recorded and the current will flow. So the two parameters, that is the current will be drawn along the vertical axis, and the VG, that is the grid voltage, will be drawn on the horizontal axis, and then of course we can have a plot of the current versus the grid voltage. And you see that since this anode is at a negative potential, so what will happen? These electrons, which are energetic electrons, when they will move towards the plate voltage, towards the plate metal, and the plate terminal being at negative potential will push the electrons back towards the grid. And so you see that these arrows in the chamber indicates the motion of the electrons back towards the grid. So what will happen is that what is the main requirements is that the voltage that we apply, the grid voltage should be, since the grid voltage will be increased from 0, so we shall keep on increasing the grid voltage, and we shall keep on noticing the current I. Initially the current I will be 0, so we shall keep on increasing Vj. A stage will reach when the voltage Vg will be such that the kinetic energies acquired by the electrons which are accelerated towards the grid G, their kinetic energy will be given by E times the voltage Vg. So electronic charge E multiplied toward the grid voltage Vg will give you the kinetic energy of those electrons. So these electrons will move with such a kinetic energy. But if the kinetic energy of these electrons, which is represented by E times capital Vg, is equal to or greater than at least equal or fairly or at the safe side should be greater than the ionization potential of the mercury atoms, which will be we shall be representing the ionization potential of the neutral mercury atoms by the voltage Vi. I will stand for the ionization energy, ionization voltage that is required to ionize these mercury atoms. So when these energetic electrons will collide with the neutral mercury atoms represented in green dots, they will impart their energies to those mercury atoms, and the mercury atoms will be ionized, that their outermost electrons will leave the mercury atoms, and then of course the mercury atoms will be singly ionized, and those ionized mercury atoms having positive charges on them will be represented by the blue dots. And since these are positively charged mercury ions, they will move towards the anode plate A, and so initially the current is detected. So once the current is detected, we shall immediately notice that this voltage that we have applied, that is the grid voltage that we have just applied, and the energy of the electrons that they have acquired, which is equal to E times Vg, is sufficient to ionize the mercury atom. So the energy supplied to the electrons for their acceleration towards the gas chamber will be the ionization energy will be equal to the ionization energy of the neutral mercury atoms. So it means that the ionization will be decided or will be determined by the initial flow of current. Now if you further increase the value of Vg, what will happen? More there will be more energetic electrons, so more collisions will take place, and there is a more probability that these neutral atoms will get ionized, converted into blue dots, which will be moving towards the anode terminal, and so more current will be recorded. So this will be the process for the ionization potential of that one. And you see that, let me explain. So this is the battery that provides grid voltage, and you see that there is a slider over here. It means that you can change the value of Vg from very small value to the greater value, and if you want to have a greater value of the Vg, you need to move the slider towards the positive terminal. And the negative terminal of this battery is connected with the cathode, which is not shown. The cathode plate is just in front of the heating wire, and the heater wire actually heating the cathode terminal. The cathode is connected with the negative terminal of this supply, so that the cathode is at negative terminal and the grid is at positive terminal with respect to the cathode. So these electrons will be accelerated towards the grid G, and the rest of the things is what I have explained. So there is another battery, which is a separate battery, which is a high potential battery. And this battery, the negative terminal of that battery is connected with the plate A and the plate A. So the plate A is at a much negative potential with respect to the grid G, so that it can attract all the ionized mercury atoms towards it, and the electrons are pushed away from this plate, so that the current that is the current which is recorded over here in this setup should be only because of the positively charged ions of the mercury, and not because of the electrons. That is why the electrons will be pushed away from the grid, from the anode, and will be pushed towards the grid G. So let me now read some theoretical aspects of this description, of this experimental description. Electrons shown in red dot are emitted thermionically when the cathode is heated using heating coils. These electrons are accelerated towards the grid or the mesh through the positive potential Vg. Electrons then enter into the chamber of the low pressure gas. The anode is held at negative potential with respect to the plate. The anode is held at a negative potential, which I have explained. The green particles, the gas particles are shown in green. These green particles or the green dots are actually the neutral mercury atoms, or the vapors of the mercury atoms, or the atoms of the mercury atoms. The Vg, which is the grid potential, is increased slowly, and the plate current I is measured at a specific grid voltage, which we can say that Vg is equal to Vi. The gas particles encountering the electron collision are ionized, where E times Vi. You see that this is the voltage. If we multiply it with E, that is the charge of the electron, it is converted into energy. So EVI is the ionization energy of the gas particles. And the electron that will acquire kinetic energy due to the grid voltage Vg will be equal to E times Vg. And the ionization potential of the mercury atoms, neutral mercury atoms represented with the green dots, will be equal to E times Vi, where Vi is the ionization potential, where EVI is the energy which is required to ionize the gas atoms represented in green. The ionized gas particles are shown in blue, which are positively charged and are attracted by the anode held at negative potential, and the current I is detected. The electrons cannot move further towards the anode being at opposing potential, and the electrons will be repelled back towards the grid. When Vg, which is the grid voltage, is increased beyond Vi, that is when Vg becomes greater than the Vi, then the plate current I increases non-linearly with the grid voltage as shown. So now let's discuss this experiment, this plot. You see that on the vertical side we are plotting the current I, and on the horizontal plot we are plotting the grid voltage G. The grid voltage is started from zero value, and initially you will start the grid voltage and keep on increasing the grid voltage, and you will notice that the current is zero. That is almost zero current is recorded. But you see that when the grid voltage Vg approaches the value of Vi, which is the voltage required for the ionization of the neutral mercury atoms, so what will happen? The current at once becomes non-zero and will be non-zero. So this is the point that we shall recognize, that now the grid voltage is enough, and the kinetic energy of the electrons which are accelerated into the chamber with a kinetic energy equal to E times Vg is enough to ionize the neutral mercury atoms, and so the blue dots, that is the neutralized, that is the ionized mercury atoms, are produced, and they move towards the anode plate, and so a current is recorded. So the current becomes non-zero over here. So we can say that Vg is now equal to Vi. So when Vg is further increased, then of course the electrons are now more energetic. There will be more collisions. There are more chances that the electrons will, while hitting the neutral mercury atoms, will ionize them. So more ionized mercury atoms will be available in the chamber. They will move towards the anode plate, and so a more current will be recorded. So the current will be non-linearly increased with the value of with the increase in value of the grid voltage. So you see that just when the current is non-zero and the current starts increasing, we should immediately know that this is the voltage Vi that we have found. And if you multiply this voltage Vi with the electron charge, which is EVI, then EVI becomes equal to the energy that is required for the ionization of the mercury atoms, of the neutral mercury atoms represented in green. And once they are ionized, those atoms, those ionized mercury atoms, will be represented in blue. So you can see again the picture. In the picture you can see that there are green neutral mercury atoms and there are blue ionized mercury atoms. The voltages, that is the grid voltage, the plate voltage, are chosen such that the electrons entering the chamber have greater energy than EVI, that is the ionization energy. That is the energy required to ionize the mercury atoms. So the grid voltage and the plate voltage should be such that the energy supplied by the grid voltage to the electrons is greater than EVI, and that the electrons are repelled back before they reach the plate. So we will desire that the electrons should not reach the plate. That is the current that is recorded should be purely due to the movement or due to the collection of ionized mercury atoms at the plate. Now, the next we are going to present the Franck and Hertz experiment to probe discrete levels. So you see that the presence of the discrete nature of levels will be established by Franck-Hertz experiment. So this is a very similar experiment to the previous one, but the previous experiment was based on the ionization of these mercury atoms. You see that there the mercury atoms, which is the green atoms, will be ionized, and the ionized mercury atoms are represented in blue, and these blue ionized mercury atoms will move towards the plate A, and the current is recorded. So this was the experiment which was based on the ionization of the mercury atoms. But now we are presenting the Franck-Hertz experiment, which they performed in order to establish the discrete levels or the discrete nature of the levels in the mercury atoms. So the experiment is more or less the same, but there is a slight difference which I am going to explain over here. Number one is that we are not ionizing the mercury atoms. So we are keeping the energy of these electrons, which are produced which are produced by the heating coil, heating the cathode, and the cathode will produce the thermionic electronic ions through the thermionic process, and these are the thermionic ions which are accelerated by the grid voltage V. So this is up to this point the assembly is the same. But you know that in this gas chamber we have again the gas at low pressure, but the grid voltage is not increased so much. We don't want to ionize the neutral atoms, but we want the electron collisions to occur with the neutral atoms. So you see that in the first step you will see now you see that there are two types of collisions. One is the elastic collision, the other is the inelastic collision. In the elastic collisions, the electron will collide with the neutral mercury atoms. They will they will be reflected in some other or scattered in some other direction. So this scattering will take place, and in this as represented by the first path of the electrons at the top. Here you see that the electrons will not lose much energy. However, in the elastic collision, there could be a small amount of loss of energy due to the collision process. And then, of course, you see that here the electron will change their directions after colliding with each time they collide with the neutral mercury atoms, they will change their positions, and after many collisions, they could reach the plate A. And you see that here plate is also connected with a negative potential, but this negative potential is very small, maybe 0.5 volt in comparison with the grid voltage. So the plate is held at a minus 0.5 voltage at a negative potential with respect to the grid, so that it can slightly repel the electrons, and only those electrons will reach the plate which have enough energy. So all the electrons over here which are sitting at rest in this chamber should not be attracted towards the plate, but since there is a small amount of opposing potential at the plate, it will repel the electrons back towards the grid, because we don't want the isolated or the electrons at rest or the wandering electrons to be here in the chamber. We want that the electrons should not rest in the chamber and should move back towards the grid. And for that one, you see that the electrons will collide, and those electrons will have sufficient energy. They will overcome the opposing potential due to the anode, and the electrons will reach the anode plate, and then of course a current is recorded. So you see that this is the same step that we record the current I along the vertical directions, and the grid voltage is recorded along the plotted along the horizontal direction. And another type of collision is the collision that is due to the inelastic collision. What happens in the inelastic collision? That the electron have energy, they will collide with the neutral gas particles, they will excite the nuclear, they will excite the mercury atoms. So here the electrons do not have much energy to ionize the mercury atoms. They have an energy to just excite some levels in the mercury atoms. So when these electrons will excite some levels in the mercury atom, what will happen? These electrons will have given significant amount of energy to the neutral mercury atoms, by which the mercury atoms are excited, and these electrons now are left with not sufficient energy to penetrate through the distance of the chamber and will reach at the anode. So after imparting energy to the neutral mercury atoms in terms of the excitation of some levels in the nuclear in the mercury atoms, then of course the electrons are left with a very small amount of energy, and they cannot reach the plate A, and so they may be reflected back towards the grid G due to the negative potential of the plate of the anode. So you see that here the inelastic collisions are important. When you see that under the process of elastic collisions, as shown at the top, the electrons after many collisions will reach after many elastic collisions will reach the plate A. We will reach the plate A, and so a current is recorded. But you know that when some of these electrons which were reaching the plate A will encounter inelastic collision, what will happen? There will be a drop in the current. So by noticing that the current will drop and a dip in the current is observed, we shall immediately notice that the electrons have imparted energy to the mercury atoms, and some of the levels in the mercury atoms have been excited depending upon the energy of the electrons that we have arranged or that we have set up. So the grid voltage again is very important. Here we want to increase the value of Vg, but we shall increase the value of Vg from the very small amount, and you see that when this Vg becomes enough, that is the kinetic energy of the electrons is E times Vg is enough to impart energy equal to the required for the first excitation of the mercury atoms. Then of course the energy will be imparted, and the first excitation energy of the mercury atoms will be excited excited to their first excitation energy, and so the electrons will lose their kinetic energies and will not reach the plate, and so the plate current will be recorded as low. That is, there will be a dip in the current. So this is the process. So here the ionization, we shall keep the energy of the electrons in such a way that the electrons should not have enough energy to ionize the mercury atoms, but they could impart their energies in the form of excitation energy of the mercury atoms. So different levels in the mercury atoms could be excited, and then of course these will be determined by the dip in the current. So each time a level is excited in the mercury atoms, it means that the electrons have given up their kinetic energies to those mercury atoms in terms of the excitation of those mercury atoms, and the electrons due to inelastic collision are left with a very small amount of energy because they have imparted a significant amount of their kinetic energy in the excitation of the mercury atoms, and the electrons are left with small amount of energy. They would not be able to reach any more towards the plate because there is also an opposing potential at the plate, and the electrons which have not in much which do not have much energy to surmount that one will be reflected back, because during the inelastic collision, the electrons after that collision will be left with small amount of kinetic energy, cannot reach the plate A, and so there will be a reduction in the current, or a dip in the current is recorded. So now let's go through the paragraphs that relate or explain this setup. Experimental setup of Franck and Hertz for investigating inelastic collisions between the electrons and gas atoms. This is for the investigation of the excitation levels, discrete levels in mercury atoms through the process which we call as inelastic collision. Electrons shown in red dots on the way from grid to the anode can transfer their kinetic energy partially. Track shown on the top. So you see that here you can see that this is the track which is shown for the elastic collision. That is, the electrons is colliding many mercury atoms, is not imparting any significant amount of energy, but there will be a small amount of energy due to elastic collisions, and due to this collision the electrons will ultimately reach the plate A. So this is what we are talking about over here. So electrons shown in the red dots on the way from the grid to the anode can transfer their kinetic energy partially. That is the track shown on the top, or completely the track shown at the bottom to the gas atoms. So the electron will impart their energy in a significant amount of energy is imparted to the atoms as shown in the bottom picture, as shown in the picture where the electrons impart their significant amount of energy to the mercury atoms in terms of the discrete excitation of the mercury atoms, and then of course the electrons are left with the insignificant amount of energy and cannot travel further towards the plate A and are reflected back towards the grid G. And you see that when you increase the value of the grid voltage, then you see that the dip is not recorded at any voltage Vg, only at a particular voltage of Vg, where the electron energy, which is E times Vg, matches with the first discrete level of the mercury atoms. So it means that all energies cannot be accepted by the mercury atoms. Only the energy which is equal to the first excitation energy which is equal to the excitation energy of the first level of the mercury, only that energy will be accepted from the electron. So it means that there are discrete levels in the mercury atoms. All energy from the electrons is not accepted, only those energies from the electrons in terms of the inelastic collision will be accepted, which matches with the excitation energy of the levels in the mercury, indicating that the mercury has a discrete energy levels. During the elastic collision, the loss of kinetic energy will be negligible, whereas in the inelastic collision, the loss of kinetic energy will be significant. The electron may come to the rest or left with a small amount of kinetic energy and cannot keep its motion towards the anode, which is held at opposing or negative potential with a potential of minus 0.5 volt with respect to the grid potential. And you see that during the inelastic collision, every collision will not impart energy to the impart its kinetic energy to the electron. Only electrons with a kinetic energy which matches with the first, for example, with the first excitation level in the mercury. When the energies of the electron matches with the first excitation energy of the mercury atoms or greater than that one, then that energy will be accepted by the mercury atoms. The mercury atoms will absorb energy during the inelastic collision from the electrons, which is equal to its first excitation energy. So it means that this will indicate that there is a discrete level in the mercury atom and the energy, and as only a discrete energy from the electrons during the inelastic collisions has been taken by the mercury atoms. All energies will not be accepted. So it means this indicates a discretization of atomic levels in mercury atoms and also in other atoms if we generalize this. When Vg is increased, which means kinetic energy of the electron is increased, electrons may collide mercury vapors through elastic collision and may survive with enough kinetic energy to surmount the opposing potential at anode, and the current will increase with the increase in the value of Vg. That is the grid voltage. When kinetic energy of electron approaches a specific value, which is equal to n times EVR, where EVR n is an integer and EVR is actually the energy which is matches with the excitation energy of the mercury atoms. So VR is actually, R stands for the resonance energy. So EVR is actually the energy which corresponds to the resonant level in the mercury. And you know that the resonant level in the mercury means that you have excited that level and the level will de-excite with emission of photons. And when the light will come out or the photon will be emitted by such a mercury atom, by such an excited mercury atoms during its de-excitation, the light will be emitted by during the de-excitation process of the mercury atom, and that light will come out of the chamber. And if you have a spectrometer, you can measure the wavelength of light. So you can from the wavelength of light and from the energy that has been imparted by the electrons, you can find out the energy of the discrete level by measuring the absorption or the emission spectrum from the light which is emitted by during the de-excitation process of the excited mercury atoms. So let me read again. When kinetic energy of electrons approaches a specific value equal to n times EVR, where EVR is actually the energy which corresponds to the resonance level in the mercury atom, and n is an integer, they can hit n takes only integer values, then EVR, you know, that becomes a discrete value of energy. So this discrete value of energy will be absorbed by the mercury atoms which will be used in the excitation of a resonance level in the mercury atom. And the resonance level means that when such a mercury atom will de-excite, it will emit the same amount of energy that it has absorbed. That's why such a level is called the resonance level. So when kinetic energy of the electron approaches a specific value equal to n times EVR, they can hit the atoms and they can excite them. The mercury atoms are excited, not ionized. So this is important from the previous setup, that here we want the mercury vapors to be excited, not ionized, and take away energy from the electrons during the inelastic collision. The electrons may lose a major portion of their energy in this inelastic collision, and after the collision do not have enough energy to surmount the barrier, and dips are observed. in the current. So the current reduction in the current or the dips in the current are observed. Dips occur at the values when the electron energy matches with this energy of the required in the excitation of the mercury atoms, and this energy is n times EVR, where VR is the resonance voltage and EVR is the excitation energy of a resonant level in the mercury atom. When EVR exceeds 5 volt, the atom in the mercury vapors get excited at a voltage, for example, close to 5 volt or less than that one, maybe 4 point something. For example, 4.887, so exact value is that one. Here I have rounded this value, but the exact value of E at which the vapors will accept the energy, that is equal to 4 point something, 4.87 electron volt, which corresponds to the exact energy corresponding to the discrete value. So here you can make a correction over here. So this E is actually 4.87 electron volt as reported in the Franck and Hertz experiment. So when this EV, that is the energy, EVR is actually the excitation energy which is required to excite the resonant level in the mercury when the energy of the electron, which is EG. So EG is actually the energy of the electron. You see that here is again a mistake over here. This VR should not be VR, it should be EG. That is a capital G, that is the grid voltage. So when EVG, which is the grid voltage, so this R here, please replace it with a capital G. So when EVG exceeds 5 volt, the atoms in the mercury vapors get excited at a voltage which is exactly 4.87 electron volt. So also please make a correction over here. This is not 5 electron volt, but it is 4.87 electron volt, which was reported by the Franck and Hertz experiment. And in the emission spectrum, a wavelength of 2.37 angstrom is detected. The permissible resonance frequencies, resonance energies, which is equal to EVR for the neutral mercury vapors, are in the range from 4.5 to 5.5 volts. So you see that in the mercury atoms, the resonance voltages occur in this range. But whatever the situation may be, the value that will occur will be a discrete value. So it means that, for example, if 4.87 as reported by the Franck and Hertz experiment, if 4.87 electron volt is the excitation, is the energy that excites the resonant level in a mercury atom, then you see that each time for in the rest of the experiment, also that value will be followed, that the mercury atom will be excited only at that particular discrete value of energy. So it does not mean that any value is possible. So if in a setup, if one value is possible according to the experimental condition, then that value will be retained throughout the experimental setup. So each time the electron will have an energy greater than the excitation energy required for the excitation of the mercury atoms, then of course that energy will be accepted by the mercury atoms as a discrete amount of energy during the inelastic collision. So I want to make a correction in this paragraph. This when EVR is not correct, then EVG. So here R should be replaced by capital G. So this is the grid voltage, VG will be the grid voltage, and EVG will be the energy of the electron. So when this electron energy, which is EVG, exceeds 5 volt, the atoms in the mercury atoms will be excited and will accept an energy which was reported to be equal to, so E should be equal to 4.87 electron volt. This is the discrete amount of energy that is accepted by the atoms, by the mercury atoms in the chamber. Other energies will not be accepted. Each time the electron will excite the mercury atoms during the inelastic collision, the amount of energy will be E should be equal to 4.87 electron volt. Once the energy is absorbed by in the excitation process of the mercury atoms will de-excite their energy, will giving a wavelength which is equal to 2537 angstrom, and this wavelength will be recorded through some instrument, maybe through some spectrometers, and then using this wavelength you can precisely determine the amount of energy, amount of excitation energy of that particular level. Plot shown is a typical plot where accelerated electrons have undergone 5 inelastic collisions, and after each inelastic collision, the electrons will undergo elastic collisions. Accelerated electrons are not monoenergetic. So there is one very important aspect that I would like to highlight is that when you accelerate the electrons in this process through the grid voltage, these electrons which are accelerated towards the grid voltage, they will not be a monoenergetic electrons. That is, the electrons will have their energies in a short range. For example, if you have some voltage and the electrons will have the electrons, the maximum kinetic energy that an electron will acquire will be E times Vg. So there will be some other electrons will have their energies smaller than the energies of E times Vg. So there will be a range of kinetic energies of the electrons. That is, we can say the electrons do not have a mono energy. So the electron accelerated with the grid voltage are not monoenergetic. Will have a range of energies. So let me now explain the plot that this is the plot that will correspond to this setup. And you know that in this setup there will be two types of collisions. One is the elastic collision. The elastic collision will always increase the current I, because the electron will reach the plate A and the current will increase. So more electrons due to elastic collision will reach at the plate A, the current will be recorded, more current will be recorded. And when there is a inelastic collision, the current will decrease. So if there are more inelastic collision, then the current will decrease drastically, and there will be a dip in the current. That is, an immediate fall in the current will occur when there will be more inelastic collision. So elastic collision will increase the current. Inelastic collision will decrease the current, because during the inelastic collision the energy is given to the mercury atoms, which is absorbed in its excitation level, and that amount will be a discrete amount of energy. All amounts of energy will not be accepted by the mercury atoms. Only discrete amount of energy which matches with the discrete level in the mercury atom will be acceptable. Whether the electron has much greater energy in comparison with the excitation, in comparison with the energy excitation which is required in the excitation of the mercury discrete levels. So now I am going to explain this setup, which is the setup that is due to the which is the plot due to the setup I have just mentioned. So this is the plot of anode current I as a function of the grid voltage Vg. So you see that initially when you increase the voltage Vg, then what happens? The electrons get excited, and these these electrons will start reaching the anode plate A. And this is the region just before the Vr. This is the region of the elastic collisions. You see that the current is increasing when Vg is increased. So there is no dip observed, there is no fall in current. The current is constantly increasing, though non-linearly, but the current is increasing. And this increase in current indicates that this is the region that corresponds to the first elastic collision. EC stands for elastic collision. So this is the region corresponding to the first elastic collisions. So this whole region starting from the zero value of Vg to the value just before Vr is the region of the elastic collision. The electron collides with the mercury atoms and they reach the plate P, so the current will increase. But you know that when the electron has an energy greater than the Vr, Vr is the energy which corresponds, this is the Vr is the resonance potential. And if you multiply it with E, this becomes the resonance energy. that is the energy required for the excitation of the resonance level in the mercury atom, and this is the energy that the neutral mercury atom will absorb and will use up that energy in the excitation of its one of its resonance level. So this will correspond to the first inelastic collision. IC stand for inelastic collision. So the inelastic collision will occur at particular at this VR voltage. So even the electron have, you see that up to this point where the dip is noticed, in this region the electrons have energies which they can still impart during the inelastic collision, and you see that there will be a decrease in the current. It means that those electrons which were reaching the plate voltage, which is reaching the plate terminal due to elastic collision, now their number has reduced, and some of those electrons are now performing in elastic collision, giving their energies to the mercury atom in the form of discrete energy, and then of course the electrons will not be reaching the plate because they are left with insignificant amount of kinetic energies, and when they will not reach the plate, then of course the plate current will fall as shown in this region. So this is the region where you can notice a dip or a fall in the current. This is the region where the inelastic collisions are occurring and the current is falling. Then again you see that after some time, after the voltage, after the dip has the minimum value of the current will occur, then of course you will notice that with the further increase of the value of VG, that is the grid voltage, the current is again increasing. So it means that in this region where the current is increasing for the second time is the region where the elastic collisions are dominating over the inelastic collisions. More electrons are now reaching to the plate, and of course the current is increasing, and you can refer to this region where the current is increasing as the second elastic collision region. So again, when the electron energy is greater than 2 VR, where VR is again the matches with the resonance energy of the same level. So when the energy of the kinetic energy becomes greater than that one, then you will notice the mercury atoms will absorb their energies, will take away energy from the electrons, and will excite, which will result in the excitation of the resonant level of the mercury. So you see that now the mercury, now the electron has enough, now the electrons have enough energy that after one collision they have sufficient kinetic energy that either they can reach the plate terminal, or they can have other collisions and other inelastic collisions. So you see that more inelastic collisions, at least when the energy of the electrons is in this region, the energy is sufficient that it can go, that it can have at the maximum of 2 inelastic collisions. And then of course what in this is the region you see that where you can notice a fall in the current or a dip in the current. You will notice that this is the region where the inelastic collisions are dominating over the elastic collisions, and of course there will be a fall in the current. And then of course after this dip, when the grid voltage is further increased, you see that the elastic collisions are being dominated in this region. Again the current is rising, and this rise in the current indicates that more electrons are now reaching the plate, and which means that more elastic, that the electrons are now frequently have elastic collisions. They are after the elastic collisions they have enough kinetic energy that they are reaching the plate P, and this is the region of the region of energies where the electrons are have dominant energies, and they have dominant elastic collisions over the inelastic collisions, and the current is effectively increasing in this region. So in this region where the current is now increasing, you may regard this as the third elastic collision region. Again you see that when the electron energy is greater than 3 times VR, It means that the same electron now can undergo three times in elastic collisions with mercury atoms, and then of course a dip will be recorded over here again. So this will be the region of the third inelastic collisions. So this is the peak where the inelastic collision starts, and then of course in the region where the kinetic energy of the electrons is greater than the 3 VR, still the electron can impart its energy which is equal to 3 VR energy required for the excitation of the discrete levels in the mercury. So at least three such inelastic collisions can occur for the same excitation of the mercury levels, which for the same resonance excitation of the same mercury levels. And then of course you will notice a dip in the current, because now there is a frequent, that is the inelastic collisions are dominating, the current is falling, and again you see that with further increase of the grid voltage, the current is further increasing and rising, because now the elastic collisions are dominating. And similarly you can explain the other increase in the values of the current and fall in the values of the current can be explained through the elastic process, through the elastic collisions and through the inelastic collisions respectively. But remember that you should restrict the Vg voltage in such a way that Vg voltage should not exceed the ionization energy of the mercury atoms, otherwise the ionization will take place, and then of course the system will have a discretization of the system cannot be studied purely for the discretized nature level, discretization nature of the levels in the mercury atoms. So what you need to do is that you need to keep Vg smaller than the ionization potential of the mercury atoms. So you see that this plot represents indication of a discrete level which has an energy equal to VR, or the resonance level of a mercury atom. So this indicates only discretization of only one mercury atom levels. So which has a level with an energy equal to EVR. So the excitation energy of such a level will be equal to E times VR. So here it is determined that the atom has at least one level, one resonant level, which only accepts a discrete amount of energy. This is what we have established. For the other levels, there are, you see that we cannot explain this experimental setup for the other resonant levels. So only this experiment is meant only to determine only the first level of the mercury atoms. The first resonant level of the mercury atoms is discretely established in this experimental arrangement. The improved setup uses two grids at the same potential, providing a field-free space. You see that in the previous setups, you would notice that there was only one grid over here and in the chamber, so the electrons are accelerated. And you see that there is an anode terminal over here which has a negative, which is at a negative potential. So you see that there is some electric field which is existing in this chamber region. So the electric field always exists due to the positive voltage of the grid and the negative voltage of the plate. And similarly, in this setup, the plate A is at a negative potential, the grid G is at a positive potential. Again, there is some electric field within this region. So the electric field is non-zero over here. But you know that now we are going to set up, we are going to give you the story of a setup which uses a field-free region. And you can notice over here, in the next setup, over here, for example, this is the setup. You see that this setup uses two grid voltages, two meshes are at the same voltage Vg. So Vg is given to the first grid on the left, and Vg is also connected to the second grid on the right. So what happens is that there is no voltage, there is no electric field between these two grids. So this, we can say, this is the region free of electric field. So there is no electric field in this region between the two grids. So this is what we have done in order to obtain more refined and accurate results, so that we can record minor dips in our profile. And for the correct, so a minor dip can also be recorded with this setup, which has a field free chamber where the gas molecules are present in the free chamber, and where the electrons will collide them and will impart their discrete amount of energy. And we can even record a very small amount of dip due to the excitation of other levels in the setup. So let me explain this setup now. The improved setup uses two grids at the same potential, providing a field-free space. That is, no electric field is present between the two grids. This will ensure high-resolution measurement of the plate current I as a function of Vg. So you see that high resolution means a small change in the current will also be noticeable through this experimental setup because of the improved resolution of this setup. So the caption of the setup is improved experimental setup for determining atomic excitation energies of the mercury atom by electron collision. So let me first of all explain the setup, the plot. So you see that here I am plotting the current I along the vertical axis, and again the grid voltage is plotted along the horizontal axis. So I am plotting only the up to the only first dip, and then of course again the current is rising. So you see that here when the voltage, when Vg is increased, the current is increasing. With increase of Vg, the current is rising. You see that again this is a region where the elastic collisions are occurring, and the electrons are reaching to the plate voltage, to the plate or to the anode. So when the electrons are reaching to the anode, so the current is increasing. So due to this increase of current, you can see that the current is rising, and the elastic collisions of the electrons are more dominant. So what will happen when the electrons have gained their energy greater than 4.7 electron volt? What will happen? Then you will see that a dip has you can start a downfall of the current. That the current is decreasing. So in the region that the current is decreasing, this is the region where the inelastic collisions are dominant, and they are giving off, the electrons are giving off their kinetic energies to the mercury atoms, and the mercury atoms is accepting only the discrete amount of energies. And you see that those discrete amount of energies have been highlighted in small amounts of dips which are occurring. The next dip, which is a small dip, is occurring at a voltage corresponding to 4.9 volt, 4.9 volt of the Vg, and this is the dip that corresponds to another level, maybe a resonant or a non-resonant level, or an optically forbidden level in the mercury atom. And then of course further there will be a further dip in the current. And then you see that you will also notice another dip over here occurring at a voltage of 5.3 value of the grid voltage, which corresponds to another value in the mercury atom, though its cross section is very small. But of course we have measured this dip also over here, a small change in value of the current. And then of course the current will finally or ultimately decay to its minimum value, and that corresponds to a dip value of 5.8 volt of the grid voltage. So you see that this is the region where the inelastic collisions are more dominant over the elastic collisions. That is why there is a fall in the value of the current. So these electrons are not reaching to the plate. So when the Vg is further increased, you see that now with the further increase of value of the Vg, what is happening is that Vg is increasing, the kinetic energy of the electrons are increasing, and now the electrons, when the current is increasing, it means that the electrons are now having elastic cooleants rather than the inelastic cooleants, and the elastic cooleants are more dominant than the inelastic cooleants, and the electrons are, and the current is increasing. But you see that here you can also notice a small dip of current at a value corresponding to 6.7 volts of the Vg. It means that this also corresponds to some level in the mercury atoms. So then of course then the current will further increase. So you see that if you will repeat this experiment, you will always observe this type of always observe these dips at this particular value of the grid voltages, which indicates that these also corresponds to the discrete levels in the mercury atoms, and these levels are because our kinetic energies are not such that we can dominantly excite these levels. The kinetic energies are just enough that they can partially excite such discrete levels. But you see that these discrete levels corresponding to the value of 4.7, 4.9, 5.3, 5.8, 6.7, they do exist in the mercury atoms. And if you want to find the excitation energies corresponding to these voltages, you need to multiply it with the electronic charge. So you see that here you can determine many discrete levels in the mercury atoms. So a high resolution demonstration. So a high resolution demonstration of the atomic excitation energies by electron collision with mercury vapors are shown. So now let me explain this one through the paragraph. A high resolution plot is shown. It indicates many inelastic collisions along with the main collision at a value around 4.7 volt. This is the grid voltage. An intense line in the emission and absorption occurs at E is equal to 4.85 electron volt. So at 4.85 electron volt in the optical spectrum of the atomic mercury corresponding to a wavelength of 2537 angstrom was observed by the Franck and Hertz. There are optical forbidden transitions, that is the non-resonant transitions are also existing over there, which will not decay optically. So those will not decay and will not give off photons. So the photons corresponding to such optical forbidden transitions will not be noticed, but a dip in the or a change in the current in the given plot can be noticed. So where the excited only through the electron collision. So okay, so you see that there is small dips over here in over here, for example, corresponding to 4.9 or 5.3. They may correspond to optically forbidden levels. These are the levels which can be excited through electronic collisions, but they will not give off their energy optically. That is, they will not emit photons, and since they will not emit photons, we cannot measure photons. We cannot measure wavelengths corresponding to those levels. But at the tips, we can notice that of course some levels will exist corresponding to these voltages, and these levels will always exist if you repeat these experiments, which indicate that there are discrete levels in the mercury atoms. Now let me explain something about this experiment in terms of the paragraphs. Electrons acquire more uniformity in energy in the field free region compared to the previous two regions, compared to the previous two paragraphs, or compared to the previous two experimental setups. A structural detail in the output can be seen in the current voltage curve, which shows a further excitation of the atoms. All the maxima are not correlated with the observed spectral lines. Optically forbidden excitations are possible through collisional excitation. That is, you can collisionally excite optical forbidden excitations, but they will not decay by themselves. Either they decay through electron collision, which will not give off any light. The energy of a free electron is not quantized. If an electron's energy is greater than the excitation energy of a level in mercury atom, the mercury atom is excited to that particular level, and if the electron survives with enough kinetic energy, it can also excite other atoms to on its way. That is, multiple inelastic collisions will be possible. The discretization of states in an atom are thus established through collisional excitation. Electrons acquire more uniformity in energy in the field-free region. Excitation by light requires that the energy of photons must match the energy required to excite an atom to a required level. So you see that in the 2 days, if you want to perform this experiment today, you will perform this experiments not with electron collisions but with precise laser wavelengths, because the laser wavelengths will be known and you can selectively excite the levels. All the levels which can be excited, but of course the optically forbidden levels will not be excited. Those will only be excited through electron collisions. So this was all about this presentation, and this is the end of slide number 5 of the course on atomic and molecular physics.